Good morning, everyone. I want to welcome our generous sponsors from Carstens, Bane Carstens and his daughter Julia Listner. And they will be making a presentation today about a technology that has been fundamental to our understanding of speech production for many years, and that is electromagnetic articulography, or EMA. And without further ado, I turn the presentation over to Julia.
Thank you very much, Mark. Hi, my name is Julia Wiesner. I'm the daughter of Bane and Brigitta Carstens. And from me also, welcome to the sponsor presentation of Carstens Medizinelektronik. It's a very special pleasure for me to be here today. I've joined several conferences during my childhood, and the last one has been a bit longer. And this is a special pleasure for me to be here today, which is only possible because this conference takes place in the virtual world. So I'm very happy to be here with you. And another thing why it's a pleasure is because my father, Bane Carstens, is going to tell something about the history of the EMA, which you can imagine is closely linked to our history. We, as some of you may know, we're 6 siblings at home, and we always said that the EMA system is kind of a 7th sibling, which we had to share a lot with, but which we also profited from a lot because we came to travel and was very much fun. And this is why this is a special event for me today. We brought something that we want to tell you about, and so I'm now gonna start my presentation here and later give the word to my dad. So I hope you all see now my little presentation that Bane prepared. It's about electromagnetic articulography from the beginnings to today. And this, here you see some of the beginnings. This is the very first workshop back in 1995 in Stockholm. And this was a live event. There you see the people around, which is not possible today, sadly, but has also some payoffs. What you see here is that when we came to that conference, we had a camper packed full with food and drinks that we shared with the people that joined the workshop, which is sadly not possible today. So all we can do is show you the picture and hope that you enjoy the picture at least. What we can still do is show you some demos and pictures and tell you something. The first thing we want to tell you about is that the new EMA system, we made some developments to get the system more handy, to have it transportable. Here you see that we can reduce the size of the system so that it fits through a door. Here you see the normal door has 820 millimeters, and now with some amendments, the system can fit through that door. And here you see some pictures of how the system is packed in a vehicle. Here you see again where you can do the amendments to reduce the width to 765 millimeters. And here is the device that makes the EMA system very easily transportable. So you can see that one single person here, the employee Ines, can load the system into a vehicle to take it anywhere you like. And another idea that we're working on is to install a dual system in a camper, which is possible because a camper has a lot of plastic instead of metal. And then you can imagine that you can just take the system anywhere you want to go with it and test people in any place. So this is some future perspectives. And from future perspectives, we now want to go a little bit back to the beginnings. And Bane is going to tell you something about the history of the AG500 before 1881. So now I'm going to stop my presentation and my dad's going to take over.
Yeah, thank you very much, Julia, and welcome to everyone. I have to start to share my screen. So, and hopefully you can see my presentation.
Ja.
Ja.
Nee, man sieht immer noch die Referentenansicht. Wenn man noch den.
What's missing?
This is you're showing the man sieht die Referentenansicht. Also den anderen Bildschirm.
Oh. So I have to stop. Let's tile. Do you see now the first slide from my presentation?
Looks good.
Okay. So when we started the development from the AG100, we found 3 other systems available. It was first from Osamu Fujimura, the X-ray microbeam system, and we are very proud that this scientist visited us in 2000 in Göttingen. And there were other devices were Joe Perkel and Paul Schönle. They made the EMMA system, where we had the job to make this available as a commercial system. Here's a look to Osamu Fujimura, his device. Oh. So his device is the X-ray system, but produces a micro beam X-ray that was focused on a pellet on the tongue, and it was always adjusted that it follows the pellet. It was, as you see, it was a very big system and also expensive. And then I had the idea for the event in Providence that we bring together all grandfathers of the articulography together with our customers and prospective customers. And but it didn't work because we are now online. So, but Joe Perkel sent to me his publication where everything is described. He describes here what he had and what Paul Schönle had, and that was what was the basic for our development. So that was our first prospect in 1988. We built, if you look here, Joe Perkel had 2 systems, one with 2 transmitter coils and one with 3 transmitter coils. And this another version with 3 transmitter coils had also Paul Schönle, and we had a cooperation with the University of Göttingen that with the goal that we could offer a commercial system. And that was the AG100, in principle the same as the version from Paul Schönle and Joe Perkel, but more plastic and a little bit optimized. So, and the first system, one of the first systems was delivered to Phil Houle at the University of Munich, and Phil will now talk about his experience from 1986 until now. He started with an AG100 8500, our first system, and now he has 8500, two 8500 devices, so he runs a dual system where he can observe how people talk to each other. Yeah, and so may I give over the talk to Phil? Okay. Ah, Phil ist da.
Yeah, I'm here. Yeah.
Dankeschön. Thank you.
Okay, I just need to see where my share screen has got to. Yeah. Okay, yeah, so when I saw in Barna's notes before the meeting, it's going to be about 35 years, and I thought, okay, everybody's going to expect, well, it would be a good idea to turn up with a long white beard or something and with a walking stick and just talk about what things were like in the good old days. What I did discover was by mistake on the Gather Town, I gave myself an avatar in a wheelchair, which was probably just an indication that my eyesight's going, but I fixed that eventually. So yeah, this is going to be a kind of very informal look through some of the main stages, how I've perceived it. As I'm going to be jumping a little bit to and fro because I just didn't have the time to get everything into a full-scale presentation. I'm going to leave it like this so I can switch between different views easier. If it's too small, then just send me a rude note or something and I'll change. So yeah, as Barna said, it started with the AG100. I don't know if you can pick out the cheerful subject in this particular view. It shows one of the disadvantages. It was quite uncomfortable, this helmet, as it had to be aligned with the midline of the subject and wasn't allowed to move around much. So it was quite stressful for the subjects. There were various devices for sort of counterbalancing it, hanging it from the roof. For example, this was Joe's setup. I know that in our late lamented friend Eric Bateson's lab in ATR, this device was by an ingenious pulley system, which involved plastic bags filled with back volumes of jassa as a kind of counterbalance system, just to take a bit of weight off the participant's head. So the serious point here is simply, obviously, there was a need to make it more comfortable for the subject. And this got us into the AG500, which was going into 3 dimensions, or as I'll emphasize later, it really should be seen as 5 dimensions. And looking back at it over the years, I would say actually what was more important was it was more important for the subject comfort rather than for the 3D aspect as such, because I would still say the vast majority of studies are still measuring articulation on the mid-sagittal plane. But one thing this device did open the door to was to also regard head movement as part of the communication process, so not just as something to be factored out, but something that can also be interesting. And I'll just mention a couple of examples right now, even though I would say that robust tracking of head movement wasn't really achieved until the next generation, the AG501. To just show you what I mean by head movement, here's a first video.
Scheiße, schwierig.
And I don't know how good your colloquial German is, but I wanted him to go through the main degrees of freedom of head movement, and he's saying, gosh, this is a difficult task. And with some of the rotations, he's having a little bit of trouble. But this is just to demonstrate that, what we really need to do, or what we could then do, was to extract the 6 dimensions of head movement. And okay, maybe this movie, while I've got it here, this basically shows the 6 dimensions of head movement systematically. So the 3 Cartesian dimensions and then the 3 rotational dimensions, just as a proof of concept that you can actually pull this stuff out. And this is what needed to be done then in order to actually make use of the data. And where it actually becomes useful, in addition to, as I say, just factoring it out, we did a mini study on head movement accompanying tone production in Mandarin. Other people have done that in the meantime. So it's certainly not the case when you say tone 3 in Mandarin, that you really imitate it with the head, but there does seem to be some systematic link. Maybe a more typical example, just an up-to-date one, but other people have done similar things, is a very obvious thing that makes sense to do is to look at links between head movement and prosodic phenomenon like focus. So this is just an example that Krista did here at this meeting. The other aspect that leads on to is entrainment between different systems. So this is an experiment I really liked by Mark and friends, where they did something really pretty sadistic, I think. So a lot of you know the top cop experiments where you have to say top cop. And if you do it faster and faster, then it, you know, there's bound to be problems. And this showed quite neatly, I think, how head movement would kick in and in effect synchronize and then train probably to stabilize the system when the task is getting tricky. So this is, I think, a first neat area of how you can diversify once you start moving into 3 dimensions. Then, yeah, after we get out of the difficult adolescence, we got to, I would say, the mature system, the AG501. And the important thing here is it wasn't just an incremental change going from 500 to 501. I went into that in quite a bit of detail at a meeting quite a few years ago, so I'm not going to repeat that here, but just there's lots and lots of evidence about how much more robust it is. And the reason is really very simple, because simply I say simply, it was a big engineering feat, but increasing the number of transmitters from 6 to 9 simply made solving the system of nonlinear equations so much more robust. Then it got rid of a lot of the stuff we really had to wrestle with. And this could be the point in the talk where I really go into sort of old fogey mode and say, you know, you young kids, you just don't know how tough life was 10 years ago. We really did have to work really hard with the AG500 to get good data out, and we did get a lot of good data out. But so instead of going into the old fogey bit, I'll just show you an example of some of the data we did get. Sorry, that wasn't the one I wanted to show you. A bit of an example of connected speech.
Der nette Schotte hat eine schwarze Socke verloren. Der nette Schotte hat eine schwarze Socke verloren.
So this is a German sentence saying the nice Scotsman has lost a black sock, and there was an important reason for that, why to use that in studying connected speech processes, which I won't go into now, but the anecdote I always tell the students about when I'm introducing them to connected speech processes is that, yeah, the AG500, it wasn't just a lot of trouble. We also did get a lot of good data out of it and had a lot of fun. And part of that was when we got invited to take part in the television show on a sort of science program. And they wanted to actually look at speech recognition, but there's not much to see there. So they decided to show this kind of stuff because it's just kind of, yeah, looks better on television. So we got the nice Scotsman onto television. And the funny thing about the program was, in the end, our part of it was kind of sandwiched between contribution about new kinds of condoms on the one hand, and volcanic eruptions on Etna on the other hand. And in between it, we had the AG500. And yeah, I suppose you can say this is kind of the phonetic equivalent of doing a press conference between a garden center and a sex shop or something. I don't know. You know. Anyway, back to the slides. So, as I say, the AG501 was, I would say, the mature system. And in a way today, I'm really talking about the kind of the bits around the edges, because you all know enough about what you can do with the tongue and so on. So, for example, once you're getting a robust system, it also means you can expand the measurement area. So it made hand movements feasible to a certain extent. This had already been done with the AG500. I think they did it by having people, you can see that tapping up around here, so quite close to the other sensors. What we've started to look at is more kind of this location for looking at tapping, synchronizing with speech. And this is the kind of location that's still feasible. This also means that, for example, you could, to a certain extent, look at musical instruments, which we have done. So we've recorded people with a a clarinet in their mouth, and you can record it, for example, the position of the instrument, like how they're holding the clarinet, for example, or even potentially perhaps their fingers. And this gives you a rough idea of probably the kind of measurement region that still just works. You just have to realize that the signal does decline very sharply as you move away from the transmitters. It's as it was in the early days, still a cubic relationship basically, so it does decline very quickly. So it means you'll get a fair bit of noise coming in if you go further away than that. But this kind of region does still seem to be just about feasible. Yeah, and in parallel to the kind of, in effect, the normal developments going through the various generations, people obviously started to look at dual EMMA setups, and this has also gone through various manifestations. So in Edinburgh was probably the first one. They used two AG500s, but had to put them in different rooms quite a long way apart because of the interference. I think at that time you needed about 6 meters difference, so you couldn't really have subjects interacting directly. Then something about that time, also a really neat idea, was to combine a Carstens system with the competitor system, because they also don't interfere, at least not electromagnetically, and enables you to record two speakers simultaneously. The most robust way of doing it now, I would say, obviously, is to use two AG501s, because you can configure the transmitters so that they don't interfere, given, say, a subject separation of 2 meters, which is now perfectly normal these days. So this can be regarded as absolutely normal interaction. And yeah, we have this kind of setup, and quite a few other people do as well now. Clearly, there's a good market for studies of convergence. So just a couple of hints here. Other thing about this setup, it's really great for triggering speech errors. This actually goes back to the original example, that maybe the first version that was done in Marks, I think in Sydney, with their setup, where they were getting people doing the famous top cop stuff, but two people doing it together. And I'll just show you briefly what that looked like in our lab.
Töpfe, Köpfe, Töpfe, Köpfe, Töpfe, Köpfe, Töpfe, Köpfe, Töpfe, Köpfe, Töpfe, Köpfe.
So the basic idea was the first subject has to say Töpfe, Köpfe, and the second subject at the same time says Köpfe, Töpfe. And I won't go into any results here because that's not the purpose of this talk, but this is really a good way of getting these typical interferences that lead to intrusive gestures and stuff like that. And this is something that they tried out in Marks quite a few years ago, and we kind of latched onto. And I think that's really quite a neat idea for this kind of setup. Another strand, maybe a slightly more serious thing, but I think actually really central, is developments in experimental control. There's been a kind of zigzag course, because actually we were quite early able to get real-time display in the AG100. This was partly at the time thanks to Joe, because even that system originally wasn't, the solution of the equations didn't have a closed form and had to be done iteratively. But at MIT, they came up with an algorithm to do that quickly, and then Barna came up with one shortly afterwards. That made us able to build real-time display into the AG100, also partly because, as Barna had always made the software available, which was extremely useful to us at the time, we were able to simply slot it into our own version of the acquisition software. And real-time display is obviously really useful, and we went through a phase with the AG500 where it wasn't possible, and this was really tough because also the position calculations was quite slow, and I would run around the lab like a nutcase, getting the position calculation running on as many machines as possible and hoping that enough of them would provide some data so we could have some idea of whether the acquisition was working okay or not. Clearly, this has also become much, much better. So most of you will be familiar with the real-time display in the normal AG501 software, and this is great. What in a sense is perhaps almost more useful is the fact that as a user, you have the opportunity to access the status of the system via TCP/IP connection. And I think Barna is in the process of setting this up for Python framework, which means basically from any computer you can control the system, you can control the notebooks running the AG501s, and you can inquire into their status. You can cause them to start recording, stop recording, but also get information on the status of the sensors. And this is really useful for any large-scale experiment where you want to get through lots of material without having to worry too much about whether the stuff is working or not, and also monitor automatically whether it is working and log it without having to use pen and paper. It's almost even more important for dual EMMA configurations because you have maybe up to 20 or even more sensors to take care of. I don't know if you can see it in this. I'll just try and explain it briefly. This is kind of what our investigator would be seeing. It's kind of my MATLAB interface to the actual AG501 control computers, and I'm basically sucking up the information they use themselves to give an online real-time display of the quality of the data. So this is a kind of traffic light scheme as to whether the data is in the main part of the measurement area or not. So it goes red if you're outside the measurement area. It goes red if other quality control measures turn bad. And the really neat thing about this, it's not as spectacular as a real-time animated display, which is also possible, is that it also keeps a record of the worst data quality that has occurred since the last trial began. And this is really good because if you imagine a situation where somebody's managing to bite on the leads to the sensors and stuff, and the lead is starting to go, you may not actually notice that immediately because it may be just causing dropouts for very, very brief periods. But if the system is providing you with the worst case that has occurred, it means you're going to catch that even if it's just occurring very, very briefly, which you may well not catch by eye in a normal real-time display of the actual sensor movements. So this kind of information, I think, is really very, very useful to be able to have it and to be able to monitor it from, in effect, from your own computer setup. So you can set it up to run the experiments as you like and still monitor the hardware. Even means if you wanted to, you could get your students to run experiments and you go and sit in your office and monitor the course of the experiment from your office because you can see what's going on via the TCP/IP link. Yeah, so we're now gradually getting into boring middle age, I would say. We have come a long way. Do we still need to do more effort to standardize and normalize our procedures? Many of you probably saw the poster yesterday, and what that boils down to is a forthcoming paper by Rebenik and others, where they very usefully reviewed data collection practices, in particular how people go about gluing sensors on and how maybe we should be more careful about specifying how we think we're going about it. So this is one direction into increasing standardization in a sense, or at least making people aware of the issues. This is certainly useful. There are maybe a couple of additional points, partly related to the gluing procedures. As I said earlier, perhaps, I still think it's not really sufficiently appreciated that this is a 5D system. This should be taken into account when deciding how to glue sensors to the articulators, because you have a choice about how you can orient the sensors on the articulators, and depending on how you do that, it has an effect on the orientation information that you can then get out of the sensors. So for example, you have a choice for the jaw, whether you glue the sensor in such a way that the orientation information is going to give you information on the angular changes in the jaw or not. And similarly for the tongue, whether you're getting angular information along the midline of the tongue or not. It depends on what you want to get out of the experiment and how to optimize the information you can get out. And for the head correction, it can be absolutely essential. So maybe I Yes.
Der nette Schotte
Sorry.
hat eine schwarze Socke
I've had
verloren.
enough of the nette Schotte. Scroll back up, go back to the original one. So this is the front view of the two sensors on the upper incisor and the nose, which I think are the most useful positions for the reference sensors. These lines here are determined by the orientation information from the sensor. And if you want to use those two sensors for doing the head correction, and often this is, I think, the best solution, then you absolutely need this orientation information. So it means you can't glue the sensors at right angles to that orientation. You can't glue them so the main axis is going like this, because you'll lose, in effect, one rotational degree of freedom. And that's where it really becomes obvious that you need this rotational information. And I think in a sense, it also makes sense to think about using it, because if you imagine a worst case situation, this is an extreme example of someone doing a kind of retroflex. If you have three sensors on the tongue, then you can probably capture the whole retroflex movement. But if you imagine the middle sensor had dropped out, or for some reason you just couldn't use three sensors on the tongue, then the orientation of the sensor, which you can see here, is really giving you a lot of additional information. I'll just play that again. Okay, and I've actually been pushing people for years to try and use this orientation information. And to be honest, we actually haven't really come up with a really good case where it actually is adding a lot to the information you can extract. But I think there are quite a few cases where you can imagine the worst case scenario where maybe sensors fail, then it could really give you the crucial additional information you need with, in effect, with less sensors. Okay, left blank to remind me of the movie demos, which I had remembered. That was what I just showed you. Just almost finished now. A couple of topics that aren't talked about very much. Coordinate systems. I think it's important to be aware of what you're using and what other people are using, because they're not God-given. We use this particular arrangement here. X-axis is the transversal axis. Y is the anterior-posterior. More posterior increasing, being more positive. We have very good reasons for this. First of all, it makes it look a bit more like anterior posterior, a bit more like on an IPA chart, but it is rotated by 90 degrees relative to the raw Carstens arrangement. And I've no idea what the NDI system uses. It's just important to be aware that it's not something that's God-given, and you can assume that everybody else is using the same thing. One reason we happened to use this arrangement was because it matched up with the arrangement we were getting from MRI data at the time. This actually is a very long-standing issue. I can remember discussing with Joe years and years ago. We were also showing posterior to the right, and I think Joe was showing it the other way around. And then we simply agreed that the subjects all looked towards the Atlantic. Which is very kind of, Western centered. Obviously it excludes everybody working in Asia. So that obviously didn't have a great future for itself, but that was our way of rationalizing it at the time. Yeah, another subject not talked about a great deal, I think, how to acclimatize subjects to the procedures. I think the EPG community has done more of this than we have. I think it's a really good idea to get subjects into the lab before the experiment, give them maybe half an hour's experience of a sensor on the tongue, get them to talk with the sensor on the tongue as much as possible, and then maybe come back later for the actual experiment. And I think in a way, this setup here is actually not too far removed from what we have in an EMMA experiment, particularly if you're combining it with other stuff. And that is, something you can't expect to just be able to pull subjects off the street and expect them to give you good speech data. So finally, now we got through the whole lifespan. Looking back, this is kind of a big word here, democratization, which I can't even speak. I think that is what this has provided, and I think it's really great that Barna has managed to keep going through all these years, because I think it is extremely beneficial that so many more people have access literally to the tongue. And I think, yeah, you can call it something like democratization. It's really, really educational for the field that people aren't just taking data secondhand, but are actually able to do it themselves. And when we were starting to do it for us, it was quite a new idea that we could actually consider gluing things on the tongue. We knew kind of Joe could do it, but we weren't sure we would be able to do it ourselves. But I think by now, people regard this as a perfectly normal thing to do if you're interested in speech. And I think this is really a good thing, because I don't think you should be, if you're studying the tongue, you should be getting away from looking at it as a kind of, just the kind of typical mid-sagittal sketches you get in all the textbooks, but really actually literally getting to grips with it as an organ, and being forced to, yeah, really be able to deal with it and understand how the organs actually behave in practice. And the fact that this is now much, much more freely available than it was these 35 years ago, I think is really an enormous advantage to the field. So looking into the future, but only very, very briefly, this is what our present looks like at the moment. And I just hope this is not going to be the case for too much longer, but at the moment we can do recordings. Of actually not right at the moment, but in principle we can do recordings like this. But I hope this is not going to be the situation for more than a couple more months. So yeah, thank you for attention. And I don't know whether it's appropriate to ask for questions, but during the rest of the conference, I'm happy to exchange ideas with anybody who's interested. Yeah, so I'll exit my share, I think. There you are.
So thank you very much, Phil. It was very impressive. And I think always if we have questions from customer where we do not know the answer, we forward the question to you. Thank you. So now I'm dran. So yeah, thank you, Phil. And the next we have the thing what was very early. I think might have to start my presentation. Sorry, I have to share my. Yeah.
There are some questions in the questions and answers. Do you want to have a look, or later?
No, first we can go to the question and answer, then I have time to find my presentation.
Okay.
PowerPoint. So, oh, is it the right way now?
Yeah.
Mm-hmm. Yeah, perfect. Okay. So now shall we answer to the question? Who will answer to the question? Phil, will you? Or shall we do it later?
Well, okay, I think a couple of things we can just cover very quickly. Okay, Bernd Kroger about Python, probably you need to talk directly to Barnett about that. And there's just a couple of notes from Martin about the paper I mentioned with the methodological study. So basically people just need the links. So I don't think we need, I assume we don't need to go into that in detail. It's just for information. There's a question, Tino Stering, about smoothing percent. So this is really, I think, a completely separate issue, which we can't go into here. I did go into that a little bit in my presentation back in 2014, I think, because it's certainly a serious issue. I think people do have a tendency to smooth too much, but basically the raw data is always available, at least with the basic sample rate, and the AG501 can you provide you data sample at over 1,000 hertz with basically initially no smoothing, and really the smoothing you do is up to you. And this is a really big issue, which honestly I don't think we can go into here. And also a question about the TCP/IP protocol while reading censored data. Does it have the timestamps attached? That I don't think it does, because it basically just gives you as much data as as it manages to sort of push out in real time. And over a typical TCP/IP connection, this is probably going to be about maybe about 10 times per second, so really designed for real time series analysis. It could give you a rough idea, for example, of potentially of whether the jaw is currently high or low, for example, to potentially perhaps trigger something else. That's one thing that occurs to me. But that's why I emphasize that in the background, and this is separate from the TCP/IP stream of the real-time data, is that the local processes are recording the worst case that has occurred. And this is why I think that's so important, because it's independent of whether your TCP/IP connection can provide you data at 10 times per second or 15 or 25. It's always going to be slower than the actual data rate, but at least the system can give you information on what was the worst case that has occurred since the last reset, and that's at the full data rate. So that's, I think, is really useful. Is there anything else we need to go into here? There's a question from Lisa Goffman about applicability to young children. Yeah, I'm not sure there's a quick answer to that either. Maybe I would suggest people who have experience with recording children should maybe get in touch with her or somehow make themselves known, because we've done it a little bit, maybe sort of around 6, 7-year-olds. I believe some people have tried younger, but that's also obviously a kind of a big topic of its own. Yeah, I hope maybe that covers a brief response to most of the things. I guess there are quite a few things that would make sense at the end of the session to just decide if there's time to carry on discussing other things in detail if anybody wants to, or say these are something we need to meet outside the session to discuss further, because as I said, some of them are quite big issues, like smoothing data, what's going to work with young children and so on. Yeah, okay.
Okay, then I try to share my screen. So my next topic is contacting our customers and prospective customers via AGWiki. We have a wiki since a long time, and
excuse me, Bana, but you're not sharing your screen yet?
Not. Oh, okay. Yeah, here it's. Now it's there. Is it right?
That's it. Yeah.
Perfect.
Okay. But I like to increase the communication with customers, because their ideas, when we realize their ideas, we develop our system in the direction that the customers have advantages from it. And as Phil said, we have provided a program template that controls the AG500 over TCP/IP. This program only does all commands that are necessary to start a sweep and stop a sweep. So a programmer can look inside this program template and see what is necessary to give commands and what is the reaction from the AG500 of each command. Therefore, we established a user portal, and we had topics, ideas for improvement, if anyone wants to give us an idea or discuss. And then another page shows which devices can be connected to the AG501 or AG500. And the AG software community, that's our idea to set up, to build, let a community grow, that customers who are, do programming and together with us develop programs that are available for all and for free, of course. And what we can commit is our info about the AG501 or AG500, and customers can bring in what's their need for a good running program. Another thing is we can give information on our internal electronic that is available on AGWikis. You can see which components are in the central electronic and what we can develop. It means that our parts, they are there but not used. So some parts only need software to get it running, and other parts need hardware development. And I like to get a community so that we can talk about what's the best to develop. Another thing is there was founded a Articulograph International Steering Committee, and here you can read what Pascal van Lieshout told, because he has another job and is head of the department now and has no time to do this job. And so if the people who hear me now, if one of you is interested to become the leader of this committee, please contact me, or otherwise use look for your colleagues, that the customers build a group that is talking to us. So the ISC should care of the interests of customers. And please think about, we have a market position now, the competition is gone, and so we can get lazy if we have no competition. So please help us that we do not get lazy. So now I have another thing is when Burkhard was for 3 months in Dallas and has developed a program together with Bill Katz to treat subjects with problems with tongue movement. In the meantime, the software is definitely improved and adapted to a 3-dimensional system, and this software is now available, and I will show a video from Bill Katz. Therefore I have to stop. Oh. Okay. So.
Hello, my name is William Katz. I'm from the University of Texas at Dallas.
Kommt das an?
I appreciate the invitation by Bonnie Carstens.
Not sure.
No, only the sound, not the video.
Not the video. Oh, okay, okay. Again, I have to share. Yeah. So. Now the video is.
Yeah, it's good.
Hello, my name is William Katz. I'm from the University of Texas at Dallas. I appreciate the invitation by Bonnie Carstens to participate in this seminar on electromagnetic articulography. I'm going to briefly describe some software we've developed for research and subject training based on a real-time tongue avatar. I'd also like to thank Anthony Long and Hiranya Kumar, 2 of our students in computer science and engineering, who have recently contributed a lot to this project. The inspiration for this software, which we call OptiSpeech, came from early work back in the days of 2D Emma, when we found that visual feedback for tongue movement seemed to help talkers with apraxic speech reduce the frequency of their speech errors. At that time, we used a DOS-based program that let us conduct some basic feedback experiments. With the advent of 3D articulography, which brought better precision and graphics, we decided to develop some additional tools. So we at UTD Collier formed a partnership with Volintis LLC, a Dallas biomedical startup company, and received a Small Business Initiative Research Award from the National Institutes of Health. In the first phase of this funding, we developed the software. In the second phase, the product was tested clinically on children with dysarthria. This latter testing was conducted in collaboration with Dr. Janelle Vick at Case Western University and the Cleveland Hearing and Speech
Okay,
Center.
I hear it's hard to hear, to understand.
Were written in Unity 5, a cross-platform game engine used to make animated projects. Our goal has been to create a real-time workable.
I will stop the video. This video is available at our booth. Please go there. I heard it. The sound is not very good from Bill. So it's better if you come to our booth and see the video there. I will continue. So dann habe ich this is the presentation. So. So is the presentation now visible? Julia? Du hast dein Mikrofon aus.
Ja, man kann es jetzt sehen. Ist gut.
Huh?
Ist gut, man kann sehen.
Okay. Okay. So I want to point out that we have two dealers, one in China. On the booth is also a presentation from Dolly Lu, and Naonori Ito is a dealer in Japan. So here you can see the time where the AG100 was available since 1988. In the meantime, we had the AG200 just increasing the distance between the coils from 32 to 64 centimeter. And then in 2002, we have the AG500. This is Julia. At that time, it was Julia Carstens. And in 2011, we offered the first AG501 systems. So and now it was planned. So it's finished. And now I have another presentation because it was planned that Julia told until here. And so. So my talk should be the mystery of calibration for article graphs. And before we have told about the AG100 and the electromagnetic article graphs from Joe Perkel and Paul Schönle. And additional, we have the AG100 and also the microbeam system. These systems have in common that they always deliver X and Y. And nothing.
Noch nicht, ne?
Hä? Was denn?
Teils noch nicht, ne? Machst du es
Ich
noch?
zeige es nicht. Ist es nicht zu sehen?
Nein.
Hä?
Noch nicht. Ist noch teilen.
Ah, Entschuldigung. Sorry. Now it's visible?
Yes, perfect.
So the common of these systems is that they all deliver X and Y and nothing else. And the deal with physics is that you have to keep the sensors in the mid plane from the measurement device, and the orientation of the sensors have to be 90 degrees to this midplane of the device. So, and I would like to show a little bit over the functional principle. Here is a transformer, and the principle of the EMMA is measuring of distances between the sensor and the transmitter. And when we imagine this is a transmitter, this is a sensor, and we have no iron core. That means the without iron core, we have a bad transmitter, bad transformer, and from this results we can measure the distance. So the the energy that goes from the transmitter to the sensor depends on the distance, and here is the formula for that. And when we now one thing is if we follow the requirements of the physics and keep the sensor in the mid plane and also the orientation perpendicular to the midplane, then we need only two transmitter. You can see it here. If the measured signal responds to the length of the arrows here, then we have the recorded distance and see where the two circles intersect. That is the measuring. That's the result from the measuring. And if you see, if we have an error and the sensor is tilted a little bit, then the dashed lines are valid. And so you see you have an error. And so with this, you can see why we have 3 coils, because then we have a triangle instead of an intersection. And so we can calculate the error. Now I want to calibrate a system. Is the principle is to bring the sensor on a defined point, very well-known mechanical position, and then see what the measuring result is. And then trim the software in a way that it shows the same result. And so the two-dimensional article graph is a perfect measuring system. You have only to follow 2 regulations. Please keep the sensors in the midplane, and second, keep the orientation of the sensors stable so that they are perpendicular to the midplane. And why was it so hard? So the sensors must be in the center plane of the measuring system, and we only have the mid-sagittal plane from the human. This means that we have to position the helmet in a way that that is the mid-sagittal plane fits to the mid-plane of the measuring system, and the sensors need not to tilt. So, and what we need is only one more dimension. So if we had X, Y, and Z, that would be fine. And that would solve all problems. But the physics is so generous, it offers 3 more dimensions. Either you have X, Y with 2 dimensions, or you have to deal with 5 dimensions. That means we have 2 angles. And when we think about the calibration, what we have 27 instead of 9, 2 or 3D. If we have 5 dimension, we have, I think, 243 positions. That means if we want to calibrate the sensor, we have to go to all positions and then rotate the sensors once in this direction for 3 points and again in this direction. But yet now we can think about how can we rotate a sensor. We do not know where the axis is. and how to rotate them, find a mechanic to rotate them. That means it is not possible to rotate a sensor without changing its position at the same time. So it's not, for me, it's not possible to find a complete calibration. And therefore, we have the calibration unit, what we have, it does it not complete, because if a sensor runs on a circle, the circle describes all x, y, and all phi changes. But z and theta remain constant. We do not have, but we are trying to get more information from the magnetic field. For this, we have developed a test environment in the first step. In the second step, we developed 4 tools. So first I show the test environment. It was an upper part from HE500, and we had here the normal transmitter, and we were able to rotate this. We can show this pointing down or pointing up. It's again, and we have constructed arms here with a structure. That means this structure we can move the sensors here and here, and from the mechanic we do not know exactly where these positions are, but if we run here and here and here, we know the distance. If we have here 3 or 4 lines recorded, we know all lines have to be parallel and they have to be the same orientation. And from the knowledge of that, we constructed a 3D holder. That means it does nothing else than provide 3 sensors on one place on the circle, and all 3 sensors have 90 degrees difference in orientation. Another part is the 3 sliding board. This is very simple. It has a slider here, and you can move straight the 3D holder. That means we can record 18 or 12 sensors simultaneously, and we can see the straight lines. And then there's a trick,
Bane?
Yeah.
I'm sorry to interrupt, but time also goes by in the virtual world, so I'm afraid the hour is almost, or is over.
Okay.
But
okay.
you have some last few words, maybe?
Yeah, this picture, we can see with the tree slider, we can run in a way. We can run here, go back here, again to change to the other side, and here. And here you can see 2 same lines and the deviation. So then one new, we have from the HE100, we had a device to rotate the sensors, and we have modified it that we have now the same device to rotate 3 magazines. The 3 magazines have 1/2 millimeter difference to the disc, and we have another tool to position a magazine 2 times rotated by 45 degrees. Okay. So
I want to say thank you to all of our panelists, to Bane, to Julia. It's fun to see you grown up, Julia, I have to say, because we've always loved that one picture for years. And to Phil, of course. There are many questions I expect that people have, but unfortunately we are out of time. And in any event, I want to encourage interested people to visit the sponsor booth for Carstens in the gathered town environment, where they would be free to interact with you and answer the questions that you have. I guess at this point, once again, we appreciate your support very much. And I want to stress, it isn't just at this meeting, it's supporting the speech production community over all these years, because without your devices, the democratization, which I can't pronounce either, Phil, of speech technology would not nearly be as complete as it is today. So thank you very much.
Yeah, you're very welcome. Bye, thank you.
Thanks everyone for listening.